So no one decided to come to review, so I'm just going to do a couple problems that I feel like would be helpful for the test if you haven't already taken it. So the first thing that I noticed when I was going through the test myself is there is a proof on this test where we have to prove a derivative rule. And it's kind of hard, or it's not like such a hard problem, it's just kind of hard conceptually. So I thought I might do a proof of a derivative that might help you. So we're going to say that y is equal to sine inverse our arcsine of x, right? And we can just say that, well, we know the derivative because derivative rule. We know that if we take the derivative of this, it should be 1 over the square root of 1 minus x squared. That's the derivative, right? That's what we learned. That's what the rule is. But how do we get from here to there? And so there's a problem that kind of wants us to show that with a derivative rule. And so in this particular problem, we're going to take our original equation and we can rewrite arc functions like this as x equals sine y and get rid of this inverse. And so now what we're going to do is we're going to take the derivative of this function right here. And the derivative of x, we're going to do it saying y is the independent variable and x is the y is the dependent variable and x is the independent. So we take the derivative of x, becomes 1. Sine y is going to become cosine y. And then we have to remember to get a chain rule. So we're going to get this dy dx at the end. And so we can say that our derivative, or dy dx, is equal to 1 over cosine y. And this is, we're going to use some properties of triangles right here to kind of simplify this further. So our answer looks like what they want us to have, right? And so the way we do that, so we're going to start our triangle. And we're going to use this statement right here, this x, the sine y equals x. If you think about it, if we have a number and we're taking the arc sine of a number, it's essentially giving us an angle. The angle is going to be the answer. So we know that this y should be an angle. So our y is technically right here. So that's our y value. And we know that sine is opposite over hypotenuse. So if this equals x, we can just say it's x over 1, right? So we'll say that this side is equal to a. And then we're going to use some properties of triangles, Pythagorean theorem, to find this a. So we can say that 1 equals a squared plus x squared, or a is equal to the square root of 1 minus x squared. And now this is pretty simple. So we can see that cosine is cosine of y is going to be a over 1. So a over 1. So if we rewrite this, we can rewrite it as 1 over the square root of 1 minus x squared. And that's where the rule comes from. And I don't know if you've covered this, but I thought this might be handy to go through something like this before the test. So that's the first problem that I wanted to cover. The next thing I wanted to cover is kind of is using implicit differentiation and natural logs to rewrite a function. So let's say we have a function y equals x to the x squared. It's kind of an interesting problem, and we don't really have like a set derivative rule that just, well, we can say x to the x power. That's kind of weird. So we're going to use a natural log trick and some properties of natural logs to save it, to rewrite this first. So we're just going to take the natural log of both sides. And when we're doing stuff like this in a natural log, if they have something to an exponent, we can essentially just drop this down in front, right? So we can say that we have ln y equals x squared times ln x. And now we're going to use some implicit differentiation to solve this problem. So we're going to take the the dx of the whole problem. And so for this ln y, we're going to get the 1 over y, and then we remember have to chain it, so dy dx, because we're saying that y is dependent upon an x variable. And then we're going to take the derivative of this, which is going to be a product rule. So it's going to be 2x ln x plus, that would be x squared over x, or just x. Now we're just going to multiply both sides by y. And so our dy dx is equal to that. And then I'm going to use our variable up here to replace this y with actual x values, so we don't have any y's in our answer. And that's our answer. So this trick where we take the ln of both sides and use properties of ln to drop powers in front is kind of a neat trick and a handy trick to remember. So that was one problem that I wanted to go over that I saw might be kind of hard on the test. This stuff like that. And I guess one last thing I wanted to cover is a related rates problem, because I know that those are usually pretty hard. So let's say we have a cone. Volume of a cone is pi r squared h over 3. And let's say this cone is maybe 8 feet by, it's 10 feet tall and it's 8 feet across. And let's say we got water pouring at 15 feet cubed a minute. And so how fast is the water rising when h is equal to 4? And so just going to quickly run through this. So the first thing I like to do when we're doing related rates problems is just like write down stuff that we know. So basically this, but I would label this as dv dt, because that's how much our volume is changing over time. And so in this particular problem, we want to find our dh dt. And if we took the derivative of this, h is dependent upon other variables or time. So if we took the respective time, this would become out as a dh dt. But we can't really take a derivative of this function right now because we have two different dependent variables sitting around in there. So it makes it kind of hard. And so really what we have to do is we have to replace this. So they're all the same variable. And the way that we do this in this particular problem, so we're going to use some more triangle properties. But if we have this 4 for the radius, and this is 10, not 8. So this is a ratio. Sorry, that doesn't look very great. That looks a little bit better. But this ratio, 4 to 10, is essentially going to be the same anywhere on the triangle. So if we draw a height right here, and we say this is h and this is r, that ratio is going to be the same as 4 to 10. So we can basically say r over h is equal to 4 over 10. And that's going to be true for any cross-section, any radius, and any height in the triangle. And so now we have an expression that we can relate r and h, so we can replace one of those variables. And I feel like I'll replace the r. So r is equal to, that would be 2h over 5. And now we can simply just substitute out this r in our equation. So our volume is going to be equal to 2 over 15. Or no, sorry. It's going to be pi over 3 times 2 over 5 h squared times h. And so then that simplifies out. That's going to be 4h cubed over 75. And we can't forget our pi. Our pi's in there. And then we can take a derivative of this pretty easily. So if we dv dt, all this stuff is just constant multipliers. So we can just say that it's going to be there. And then we can drop our 3 minus the power by 1. So we can rewrite that as a 12 pi h squared over 75. And we can't forget that when the h is dependent on another variable, so just like this v, so when you have a dv dt, we're also going to end up with this dh dt out on the end, which is a variable that we want to solve for, right? And so we're simply just going to divide it. So we're going to plug in our numbers now. We know that h is 4, and our dv dt is 15. So we can plug in 15 there. We can plug our 4 in there, and then our dh dt. And when we solve this, this comes out to be roughly like 1.856 or something around there. You can plug it into your calculator. But when we're working with problems like this, and we have something where both our height and our radius change as time goes on, we gotta make sure that we deal with these variables, because we can't take a derivative of this right now as 2 separate variables, and so we have to change it, and sometimes it can be kind of tricky recognizing this relationship. But I guess that's it for this problem. I hope this all made sense. And I guess there's one more problem I'd like to go through. So this is an initial value problem that is basically a double initial value problem. So we're going to be working with two initial values. So let's say we have a building, and we're dropping a rock off this building, right? And the acceleration is going to be negative 32 feet per second squared. So that's our acceleration, right? Let's say that our velocity at time 0 is going to be, let's say, negative 4 feet per second. So we're essentially saying that we're throwing this rock down. So it's going to start with an initial velocity. We're throwing it straight down off the roof. And let's say that our position when time equals 0 is going to be 80 feet, right? Because the building's 80 feet tall. And I guess our question is, what's the position function? How do we find a position function out of this information? And so we're going to start, because we know that acceleration is the derivative of velocity. So we can kind of go backwards and get our velocity function, right? So we just simply take the integral and antiderivative of our acceleration function. We can find our velocity function. Well, this is pretty easy because it's just a constant. So we're just going to add our variable t. But I got to remember this plus c. That's our velocity with respect to time. Negative 32 t plus c. And so now we're going to use our initial value to solve for the c value. So we actually have a velocity function. And so the way that we do that is we just plug in our numbers. So we plug in 0 for t, and we plug in negative 4 for v. So we have negative 4 is equal to negative 32 times 0 plus c. So negative 4 is equal to c. So now we can rewrite our function. 32t minus 4. There we go. And so now we're simply just going to do this again one more time, but we're going to be using the position function, velocity, because we know that the derivative of position is velocity. So we're going to take the integral of this. So the integral of negative 32t minus 4 dt. So take the integral. So we're going to have negative 32t squared over 2 minus 4t plus c is equal to our position with respect to time. So we can simplify this a little bit, and 16t squared and minus 4t plus c equal to rp. And so now we're going to use our initial point here. So we know that when t equals 0, we're 80 feet. So we can do this again. So we just plug in 0 for our t's. And our c value is simply 80. So we can rewrite this as a function of position. And this would give us our position when with respect to time. So we could say, we could guess at any time, and it would tell us what our position is at that specific time. And so I guess on these questions, when it's just kind of important to recognize that if we're going to have two initial values, we're going to have to do the process twice. So a lot of times on initial value problems, we've only ever done it once. But on stuff like this, where we start with an acceleration and we want a position out of it, or then we're going to need to do it twice. This is kind of the only case I can think of. You can do it twice. There's probably others where we have to do it more than once. And so it's kind of a straightforward problem, but it's just kind of long. It takes a while. So aside from these problems, I think the test, I would brush up on our rules, and you can find those online, so I won't run through them all with you, but I would just brush up on your integral rules on both the hyperbolic functions and inverse tangent functions. And other than that, the other thing is this test has limits on it. So I guess remember the Hopital's rule. I guess we could give an example of that one real quick. So when we're solving with limits, let's say we have that, and it wants to find what's the limit as x approaches infinity. So when we're doing this, I guess the Hopital's rule states that if we have infinity over infinity, or negative infinity, or any variation of that, or 0 over 0, or some that we can just take the derivative of the top and the bottom to get our limit. So we can simply, so in this case, if we plug in x, we're going to get infinity over infinity as x approaches infinity. So we can rewrite this. We just take the derivative of the top, which is 12x squared plus 3, over the derivative of the bottom, which would be 45x squared plus 8. And that's the limit as x approaches infinity. And if we do infinity in here again, we get infinity over infinity. So we can do it one more time. So if we take the derivative of the top, that's 24x. That's over 90x, right? And it's the same thing. So if we plug in infinity, we're still getting infinity over infinity. So we can do it again. And if we take the derivative, that's simply 24 over 90. And there's no x's in our equation, so that's our limit. And we can simplify this, and if we take, I think, a 6 out of it, yeah, so we can take a factor out of 6, and we're left with 4 over 15. So in this particular problem, it's just going to be the ratio of the coefficients. So on limits like this, where we have the same value of the x to the raise the same value, and they're both the highest value on the top and the bottom, so it's just going to be the ratio. But that's not the case in every problem. Sometimes this might be an x squared, in which case the infinity over infinity would still work, right? Until we got to this step, right? Because then we would have 1 less x. And then we'd have infinity over 90. And so as x approached infinity, in this case, then our limit would be infinity. And so it's easy to recognize sometimes this, but it's not always the case. So just be careful on your limits. Remember L'Hopital's rule, and I think you should be good. Well, if you have any other questions about the test, email me, and hope you had good luck. Wish you good luck on the test.